So up to this point in the class, we have talked about differentiation pretty much exclusively, right? So this is the branch of calculus known as differential calculus. And if you remember in the very first video for this class, I talked about how there's basically two broad categories of calculus, which is the differential calculus and the integral calculus. So now we want to start focusing our attention on the integral calculus. And it is related to the differentiation. So, it's not a completely new topic or anything like that. It's just kind of building on that same thing now. So integral calculus is very broadly concerned with finding the area under a curve. Okay, so if we refer back to our trusty x squared example, right? Something like this. Not very symmetric. Okay, so something like this, right? So y equals x squared. If we wanted to find the area under the curve, say from 0 to say 3, right? And this would be the point 39. Then how would we go about doing that? Right, so when we think of area, the way that we're usually exposed to area first is, of course, through geometry, right? So we can find the area of things like a square, right? If the square has a side length of s, the area is s squared. If we have a rectangle with a length and a width, the area is the length times the width. Even if we have a triangle, right, and we have a height and a base, then the area is 1/2 base times height, right? So we can come up with the area for most geometric figures. But what about this kind of situation? Because if we look at this, if we try to find the area here, right? So if I just kind of highlight this area, what we'll notice is that it kind of looks like a triangle in this case, but this isn't a straight line on the where the hypotenuse would normally be, right? It's a curved line. So we can't necessarily, use these same formulas. There's not necessarily a good formula that's going to work for this kind of shape. All right. So if we just kind of look, just bringing it over, the shape, it kind of looks like this, right? Where this has like an arc to it. Okay. So what do we do in this case? Well, we basically want to build this up by kind of approximating this area using what we know about these shapes, and then continuously make better and better approximations, right? So we'll go through this in the videos, but basically we want to make rectangles underneath this area here, okay, something like this, or above them. And we want to kind of try to approximate that area. But when we do that, of course, we have this white space in the sides here. So we're not getting a perfect answer. But what we can do is we can make these rectangles smaller, and then that's going to cut out more of the white space. And we just keep making them smaller and smaller. So this is just like with the derivative, where we were finding the slope of the tangent line, right? We kept finding the slope of a secant line, and we made the distance between the 2 points for the secant line smaller and smaller and smaller, eventually letting that limit go to 0. Exact same idea here. We're going to keep making the rectangles smaller and smaller and smaller, eventually letting their width go to 0. So taking the limit of the width as the width goes to 0. Or on the other hand, you can think of it as creating infinitely many rectangles underneath the curve here. Okay. So they have kind of the same conceptual idea here. But now the second question, there's the how. There's the how do you find the area under the curve? But then there's also the why. Why do we even care about finding the area under a curve? What does this represent? We know with differentiation that represented the instantaneous rate of change of a function at certain times, right? So like in the velocity case, we could find the instantaneous velocity of an object. Well, thinking about that velocity example, let's just go ahead and let's look at, what would, let's just ask the question, how far would we travel by going 50 miles per hour constantly? Okay, so let's just assume, just for argument's sake, that we're always going 50 miles per hour, never dip above or below it, for, say 2 hours. Okay. We don't really need calculus to answer this, of course, right? We, we can just look at what this would do. We can just kind of use the units, right? 50 miles per hour, meaning 50 miles for 1 hour, times 2 hours. The units kind of cancel out here, and we're left with 100 miles. But what if we look at the graph of this? Okay. So if we were to represent this on a graph, then we would have just a constant line at y equals 50, right? So like this would be our velocity. And let's say that this right here is 2. So this is 1. Then if we were to find the area underneath this quote unquote curve, it's not really a curve because it's a straight line, but the area underneath this function for those 2 hours, okay, well, this is, because it's a straight line, this is just a rectangle, right? So we don't need any calculus here, we just need just geometry. So this height here is 50, right? Because that's where this line is, the red line. And the width here is 2, because that's the distance of this, right? So the area here is 100. And this is, of course, no coincidence. Okay, so this is kind of the idea of, why we care about this area under the curve. So we can take the area under the curve given by a velocity function, and that gives us the position function. Okay, we already know that the position function, we usually use s for position, so s of t. So this is the position, right? We already know that the derivative of s of t is the velocity. So now what we're saying with this example is that the area under the curve of velocity gives us back position, right? So in other words, the area under the curve of the derivative function gives us back the original function. And this is how derivatives and integrals are related, is that they're actually inverses of each other, much the same as logarithms and exponents, or addition and subtraction. Okay, so of course we want to be able to do this with, not a constant velocity. We want to be able to have a velocity function and use that to get back to the position function. So we want to be able to do this with a curve, right? And we just in general want to be able to do this for any kind of function. So this is the idea that we're going to explore in these upcoming videos.